Okay, AP Chem, this is going to be the answer key to the plating metals problem from the PowerPoint. So let's remind ourselves a little bit about plating metals. The variables, which Q, sometimes written as big Q, sometimes written as little q, is the charge. The units for charge are going to be coulombs. Which is big C. I is going to be current. And that's measured in amps, which is big A. T, of course, is for time, but we have to be careful because time needs to be measured in seconds. So if you're given minutes or hours, you need to convert to seconds. N, as always, stands for moles. And that's going to be, in this case, of metal ions. And then we're going to call Z is going to be the charge. That's the charge number. In general, that tells you how many electrons you're dealing with. Now, our formulas that were given to us are Q equals NZF and Q equals IT. So if you just eliminate the Q, you'll also get IT, which is current times time, is equal to the number of moles of metal of ions, the charge on the ion, times F, which is Faraday's constant. So let's add that on there too. F is a Faraday. A Faraday is 96,500 coulombs. Now, if you look in the AP reference packet, they don't actually give you all of these formulas, but I'm going to tell you what they do give you, and so we can understand why all of this is important. So the first thing that they give you is the fact that 1 volt is equal to 1 joule per coulomb, like such. And they also give you the fact that this is not just 96,500 coulombs. Actually, they use 96,485, but it's coulombs per 1 mole of electrons. So that kind of is important. The formula that they give you in the AP exam is I is equal to, and they use Q as lowercase. We're not going to let that confuse us. And that's going to be charge over time. So current is equal to charge over time. So actually, because current is equal to charge over time, you know that an amp is equal to a coulomb per second. These units can go a long way to helping you understand. So now let's go to the problems that they give us. Number 1 reads, calculate the number of moles of copper produced in an electrolytic cell if a current of 5 amps at a voltage of 6 volts flows through a solution of copper ions for 10 minutes. So what did they give us? We're solving for N. because it says calculate the number of moles of copper produced they gave us the current of 5.0 amps, and they gave us the time of 10 minutes. Let's just go ahead and say in 1 minute, there's 60 seconds. So that's 600 seconds. Now they also gave us the voltage, which is joules per coulomb. In this particular problem, we don't necessarily need that. So we're going to rearrange and solve for N. So N is equal to IT over ZF. So let's just plug now 5 amps, which remember an amp is a coulomb per second, times 600 seconds over the Z number, which is 2. That means that there's 2 moles of copper electrons. That's how many valence electrons copper has, times F, which is Faraday's constant, 96, and that's coulombs per mole of electron. So notice that amps is coulombs per seconds times seconds, so amps cancels out and leaves us coulombs. And then coulombs cancels out here. And we're left with units of moles. So 1.6 times 10 to the minus 2 moles of copper. Number 2. Number 2 states, calculate the time taken to deposit 1.00 grams of copper. So they gave us a mass. This time we'll have to convert that to moles. Into an object that's placed in a solution of copper nitrate that has a current of 2.50 amps flowing through it. And they're asking us to find the time. And that will be in seconds. Now, copper 2 nitrate gives us a Z number, again, of 2. So this time I'm going to rearrange my equation to solve for time. So that will be T is equal to the number of moles of copper times the number of the charge times Faraday's constant over I. So again, 1 gram, we'll change that to moles by dividing by the molar mass of copper, which is 63.5. So 1 divided by 63.5 gives me 0.01575 moles of copper times a charge of 2 times 96500 coulombs per mole of electrons. over the current of 2.5 amps. Now, moles of electrons, 2 is the number of moles of electrons. This is coulombs per mole of electrons. So that's why we had to multiply that by 2. So you get an answer of 1.216 seconds. That's 20 minutes, 15 seconds to deposit 1 gram of copper. Let's go on to number 3. Number 3 states, in an operating Hall-Héroult cell, a current of 150,000 amps is used at 5 volts. Calculate the mass of aluminum that would be produced if the cell operates continuously for 1 day. So we're solving for N. F is always a constant. And time is 1 day. And when you convert 1 day to seconds, this would be the conversion. Like such. So you can multiply that all the way across to get 86,400 seconds. So I'm going to rearrange my equation to solve for N again. Just plug in what's given to us. Sorry, this is aluminum this time, so the Z value is 3. Aluminum has 3 valence electrons and always has a charge of +3. To get an answer of 1.20870. This is aluminum, so it's +3. Aluminum has 3 valence electrons. We'll always have a charge of +3. And that gives us 44767 moles of aluminum. Multiply it by the molar mass of 26.98, and you get 2 sig figs. 1,200,000 grams of aluminum. Number 4 states that the electrolysis of a solution of chromium ions using a current of 2.2 amps for 20 minutes, current is 2.2 amps for 25 minutes. I'll just go right ahead and change this. 1 minute has 60 seconds. And they gave us a mass of 0.60 grams of chromium, which I will change right away to moles. Using the molar mass of the periodic table of the elements. For chromium, that is 52. Calculate the charge. This time we're solving for Z. So Z is going to equal IT over NF, like such. So now we calculated the time. 25 minutes times 60 seconds per minute is 1,500 seconds. And 0.60 grams of chromium is 0.01154 moles of chromium. So now let's plug in what we know. I is 2.2 amps. Times 1,500 seconds. N is the number of moles, which is 0.01154 moles of chromium, times Faraday's constant, 96500, and that is coulombs per mole of electrons. So multiply across the top, divide by the bottom, and you actually get a value of 2.96. But this is the charge, and the charge is equal to the number of electrons exchanged. So in this case, it has to be a whole number, and that's going to be what we consider 2 sig figs 3. So the charge on chromium in this case is chromium plus 3. Let's go to number 5. Number 5 states, calculate the masses of metal produced when 600 Faradays of charge is used to reduce the ions of aluminum, silver, and zinc. So, number 5. This time we need to use the formula that has Q in it. So, if you remember back to our formulas that were in the PowerPoint, our formula that we would use here would be Q equals NZF. That's the number of moles times the charge on the ion times Faraday's constant. In this case, we were not asked to find the number of moles, we were asked to find the mass. So let's remember that the number of moles is equal to the mass divided by the molar mass, which is grams over grams per mole, like such. That's how you get moles from mass, and that's how you get mass from moles. So let's rearrange our equation. We'll plug this in for N. So it's going to be Q equals mZf, which is mass, charge, Faraday's constant over molar mass. And let's rearrange to solve for mass. So mass is going to equal Qm over Zf. So let's lump together Q over F, that's our 600, times M over Z. So now let's do this for each of them. The mass of aluminum. So remember, Q is 600 Faradays from the problem. So if we put 600 Faradays here, divided by a Faraday here, that's our F from our formula, these cancel. and then you get the molar mass divided by the charge on the ion. So in this case, it would be 600. The molar mass for aluminum divided by the charge gives me 5,400 grams. Let's do the same thing for silver. So we lump together Q because Q was 600 Fs. And if you put F on the bottom, and the molar mass of silver is 107.9, charge on silver is 1. Faradays cancel out, and we get for silver 64740 grams. Now let's do the same thing for zinc. The mass of zinc is 600 times the molar mass of 65.4 over the charge of 2 for 19,620 grams of zinc.